Okay, the last thing we want to look at for this section, for this class, is oblique impact, and that is when the two bodies don't hit each other head on, as was the case of central impact. They come at each other at an angle. In this case, one or both of the velocities could be tilted relative to the line of impact. So how do we analyze this? One thing is, and we want to see what happens, calculate the velocities after impact, knowing the velocities before impact. So that is our goal. One thing to note here, we study cases where there is a smooth contact. The reason is that we don't want to study friction. Friction is quite complex, especially when it comes to these contact or impulsive forces because of contact. And in those cases, friction force also becomes impulsive. Friction force behaves differently. You have a stiction and a whole lot of weird stuff going on. So we don't study that. We study smooth contacts. So what do we do? Note here that if the contact is smooth and there is no friction, what color do I use? I use blue. The only forces acting on these bodies are going to be normal forces, normal to the plane of contact, and by the definitions that we had, this line is the line that passes through the center of mass and is perpendicular to the plane of contact. So this is the only force that is in the contact force acting on these objects. And because of this, see what happens. If you look at any of these particles or objects individually, the only force or impulse acting on them is along, let's call it x-axis. So you would expect a lot of things happening in x-axis because of these impulsive forces, but along y, along the plane of contact, there's actually no force. So you would expect nothing happen to the momentum of each of these particles in that direction. In other words, you can find the components of the velocity of each of these along x and y and simplify your problem. So this becomes two problems. One is body A coming head on at body B. So this is VB1X, this is VA1X. And it is a central impact problem. It gives you I don't know, something like this. VB2X and VA2X. And knowing the coefficient of restitution and the masses of two particles, MA and MB, you can calculate what happens after the impact in the x direction, the direction that is along the line of impact. In the other direction, you have this. You have VAY, and how did I draw it? This VB1Y. I missed a 1 here. And assuming two bodies are moving in parallel, without any force between them, what happens after is the two bodies will continue to have the same VA2x, VB2x, and nothing has happened. So VA2x equals VA1x, and VB2x is, no, y. All of these are y. So why do I write x? VA2y, VB2y, VA2y, VA1y, VB2y equals VB2y. Long story short, nothing happens in one y direction, and they move with the same velocity. Oops, why red? And now that you have these conditions after impact, you can calculate VB2. Let me draw it with green. No, let's do it more nicely. You have body, why is it green? You have body A, body B, and now you have calculated the components of each of these, and you know the final velocity VA2, and like this, like that. This is VB2. So separate your problem into two, one along the line of impact, then you're dealing with a central impact problem, calculate the final conditions using the coefficient of restitution, and in the other dimension, along the plane of contact, nothing happened, so velocities remain the same. And once you have the components of the velocities post-impact, you can reconstruct your total velocity vectors. Yeah, there's nothing else to this. Again, note that this is valid for smooth contact. If there's friction, everything is off. So only smooth contact. So that is all I have for impact. And we saw how we can use an experimentally observed coefficient of restitution, combine it with conservation of linear momentum during impact to get the post-impact velocities. And yes, that is, I think, enough for linear movements. And in the last bit of this chapter, we looked at another very interesting concept called angular momentum and angular impact. So I'll see you in those videos.